We begin our lecture by considering an LTI circuit. Under the following two conditions. Okay. The first condition has to do with the stability of the circuit. In other words, each natural frequency of the circuit, let's call it lambda I, expressed in rectangular form as alpha I plus j omega I, satisfies that it belongs to the open left half plane, complex plane. In other words, the real part is strictly negative. Okay, real part of lambda I, which is alpha I, is strictly negative. Okay. Now we're talking about, for instance, a circuit where the natural frequencies are at -1, -2, and -3, let's say plus minus J4, for example. Okay. Now, this implies that the homogeneous part of the solution always and very quickly decays to 0. Okay. And that has nothing to do with how you choose the initial conditions, regardless of the initial conditions. Okay. And the second assumption that we make on our LTI circuit is that the inputs, by which we mean the voltages provided by the independent voltage sources and the currents provided by the independent current sources throughout the circuit, are purely sinusoidal signals. And if we have more than one input in the circuit, then all the inputs, okay, are oscillating at the same frequency, which we will usually denote by the Greek letter omega, at the same frequency. Omega radians per second. Okay? So, for example, this is the natural frequencies of our fourth order circuit, -1, -2, and -3 plus minus J4. All the natural frequencies are on the open left half plane. In other words, the real parts are strictly negative. The second assumption, or the second condition, is that the input in our circuit, suppose that we have some voltage source somewhere, cosine omega t plus 30 degrees volts. Okay, so the inputs in our circuit are sinusoidal signals with frequency, with some frequency, okay, which we denote by omega. Now, for that, for such a circuit, any output, let's say a capacitor somewhere, will have the following voltage. Okay, we're going to have, let's say, K1 cosine omega t plus phi 1 plus the terms associated to the natural frequencies, the modes of the circuit. We have 4 natural frequencies, so those manifest themselves in our solution as K1 e to the minus t plus, excuse me, K2 e to the minus t, K3 e to the minus 2t, and plus K4, let's say, e to the minus 3t cosine 4t plus phi 4, let's say. Okay, so that's the complete solution. And this is the particular solution because it's directly related to the input. And this k1 and phi 1, they're determined by, or they're independent of the initial conditions. And then we have the homogeneous part of the solution where the unknowns are depending on the initial conditions of the dynamic components, okay, in our circuit. Now, it's clear from this expression that as time goes on, these terms all, okay, we have e to the minus t, e to the minus 2t, and e to the minus 3t, they will all decay to 0, okay? And after a while, in fact, very quickly, Vc of the capacitor voltage will converge to the particular solution, okay? So let's put that remark down. In such a circuit, okay, a circuit, an LTI circuit, satisfying these two conditions, the response converges to the particular solution. Which has the same form with the input, and therefore it's a sinusoidal signal with frequency omega radians per second. Okay, which is also a sinusoid with frequency omega. Omega being the frequency of the input. Okay. And this solution that our outputs or in general the circuit converges to is called the sinusoidal steady state solution. This solution is called the sinusoidal steady state solution. Okay. In short, denoted by triple S solution. Okay. Now, to define this concept, we're making two assumptions, and they seem to be restrictive assumptions. Okay. Therefore, this seems to be a very special case, and mathematically speaking, it is a very special case. But from the practical point of view, it's a very, very, very important case. Okay? The reason is, as we all know, that the power, electrical power, usually is generated in AC form. Okay? And it's almost always distributed in AC form. And there are many devices, especially in industrial applications, consumes that electrical power in AC form. Okay, therefore, circuits in sinusoidal steady state are very important, okay, from the practical point of view. And also from the theoretical point of view, this situation is very interesting on its own right. And due to that two reasons, we will spend quite some time on the sinusoidal steady state analysis, okay, for LTI circuits. For our analysis, we will use some very basic, simple identities. So let's list them down, and then we slowly start developing our theory. Okay. Some useful identities that will prove instrumental for our analysis and eventually for our theory. First of all is due to the great mathematician, perhaps the greatest, the Euler. Cosine phi plus j sine phi, okay? So this exponential function can always be written as a combination of cosine and sine. The second property is that this operator, real operator, or the real part operator, is a linear operator. In other words, this for two complex numbers, z1 and z2, can always be written as the sum of their real parts. Okay. And then we have the commutativity property of two operators, namely our derivative operator and this real part operator, f of t. Okay, so this reads the derivative of the real part of this complex function, f of t. It equals the real part of the derivative of f of t. Okay. In other words, these two operators can be interchanged without affecting the result. And finally, we will make use of the following property. Let omega be a real number. Okay. If real part of some fixed complex number, let's denote it by x1, capital X1, e to the j omega t, equals the real part of some other, well, perhaps some other constant, which we denote by x2, times e to the j omega t. And if this equality holds for all times t, then it must be that this x1 here must equal x2 for all t okay. Then we must have this equality, x1 equals x2. And here is very short proof. Maybe you see it already, because it also has some geometric flavor in it. If you visualize this as something that rotates on the complex plane. Anyways, since this holds true for all times, okay, it clearly holds at t equals 0. So if you plug in t equals 0, what you have is this is 1, this is 1. So the real parts of x1 and x2 must be equal to one another. Okay. At t equals 0, we have real part of x1 equals real part of x2. And since it holds at all times, let's also compute it at some other time, namely 3 pi over 2 omega. Okay. Now, e to the j omega t taken to be 3 pi over 2 omega is e to the j 3 pi over 2. And e to the j 3 pi over 2 is what? You're going 270 degrees starting from the post-horizontal axis in counterclockwise direction. So we're talking about minus j. Okay. So that means real part of minus j x1 equals real part of minus j x2. Now the real part of minus j times some complex number is its imaginary part. Therefore, we have imaginary part of x1 equals the imaginary part of x2. Now, since both the real parts and imaginary parts are equal for x1 and x2, it must be that those two complex numbers are equal. Okay. So let's call this star, let's call this double star, and double star implies x1 equals x2. Okay, so that's the end of our very short proof. Now, let's return to, in the light of these simple facts, let's return to circuits. Consider a circuit that has reached sinusoidal steady state in sinusoidal steady state. Okay, so it's not important what is the component at each branch, so we're just gonna represent them as little boxes or little triangles, and suppose that we have a circuit with 5 components. One of them, or at least one of them, is the input, and that input is oscillating at frequency omega. Circuit is stable, all the natural frequencies are with negative real parts, therefore after a while, regardless of the initial conditions, this circuit will have reached sinusoidal steady state. In other words, all the voltages and currents throughout the circuit will be oscillating at the same frequency. They will be sinusoidal signals. So let's label the voltages and currents. This is V1 and I1, and here we have voltage and current of the second component, and so on. V3, I3, V4, I4, and we have V5 and I5 for the fifth component. Okay, and input frequency, okay, or for this circuit is denoted by omega, radians per second. Okay, now since the circuit is in sinusoidal steady state, any variable, namely each voltage or current throughout the circuit, signal should look like, or should have the form xkt. Okay, this is either a voltage or current somewhere in the circuit. Xkt equals some magnitude, which we denote by a, ak, or amplitude cosine omega t, plus some phase. Now this magnitude and this phase differs from component to component, but they all share one thing in common, and that's the frequency of oscillations, which we denote by omega, and that's inherited from the input frequency. For some magnitude ak and phase denoted by phi k. Okay. Now, by looking at that sinusoidal signal, and clearly it's a function of time, we will now introduce a way to represent this signal, this function, as a constant. Okay. And it's done very simply as follows. definition for our signal xk of t, which is some voltage or current somewhere in the circuit, and all the voltages and currents they have the same form. Okay, for a signal xk of t, ak cosine omega t plus phi k. What you do is you take this magnitude and you take that phase and construct a complex number, okay, as follows. The complex number capital X K, okay, that's our notation. This is lowercase, it's a function, and this is its capital capital XK representation. The difference between this lowercase xk and capital XK is lowercase xk is a function of time, whereas capital XK is a constant complex number, and it's constructed as a k e to the j phi k. Okay, so it's a complex number with magnitude ak and phase phi k. Okay, so it's a point, it can be represented by a point or a vector on the complex plane. And this is called the phasor, okay, of the signal xk of t. Okay. Now, if you know, it's clear that if you know the phasor of a signal, plus if you know the frequency of operation, then you can construct from this pair x of k and omega very easily the signal itself. Okay, so note that given the pair, the phasor capital xk and omega, this is the phasor of xkt, and this is the operating frequency of the circuit, or the frequency of the inputs, operating frequency of the circuit. Okay, so given this pair, we can reconstruct our signal xk of t, xk of t very easily as xk of t equals the real part of this complex function, and this complex function simply is xk, this complex number, the phasor, multiplying this exponential function which rotates with frequency omega e to the j omega t. Okay, and from Euler's identity, this equals clearly ak cosine omega t plus phi k, which is the signal that we started with. Okay, now let's try to visualize this xk and through the so-called phasor diagram. And once we have the phasor diagram, this relation, that algebraic relation, will have some geometric flavor. Okay, here is the phasor diagram for a given phasor. Now, phasor diagram contains the visual representation or the vector representation of the phasor or the complex number xk on the complex plane. Okay. So what you do is, on the complex plane, real axis, this is the imaginary axis, this is the origin. What you do is you mark this phasor, you show this phasor as a vector. And what's the magnitude of that vector? The magnitude is ak. And what's the phase of that vector, or the angle of that vector? The angle is phi k. And how we measure the angle? We measure it starting from the positive horizontal axis, and we go in the counterclockwise direction. Okay, so for instance, if for our phasor or for our signal, this is the phase phi of k, sometimes denoted through the following notation: the phasor of this complex number. And here we have a vector. Suppose that the magnitude of that vector is the positive number ak. Then this being phase, this being the magnitude, and this vector here is our xk. Okay, x of k. Now phi of k is the so-called phase of our phasor or this complex number, and a of k is the magnitude. Okay, so we use the absolute value notation for the magnitude. And then once we have this diagram, it's easier to interpret this relation, or to talk about this relation. So what we have is, we have the phasor, and from this vector here, xk, and from this vector xk, given the information about the frequency of oscillations, we will now generate the signal, lowercase xk of the time domain function. And here it says that take that xk, multiply with e to the j omega t. Now, if you multiply any vector with e to the j omega t, note that the magnitude of e to the j omega t is 1, always. Okay? What it does, what changes is its phase. And what it does is it rotates e to the j omega t, or whatever it multiplies, it rotates with omega radians per second. That means every 2 pi over omega seconds, it completes one full rotation. So it will rotate, this xk multiplied by e to the j omega t, it will rotate with omega radians per second. And then, okay, so that's, as time goes on, this times e to the j omega t is this thing rotating in counterclockwise direction. And then from that rotation, or from that rotating object, we obtain xk of t by real operator. Now what's real operator? Real operator is simply, you give me any vector, it's the projection of that vector on the horizontal axis. So as this guy rotates with omega radians per second, okay, its projection on the horizontal axis, let's take it as a point, it will oscillate back and forth between plus and minus ak. Okay, and if you mark all those points, okay, points on the horizontal axis that's oscillating back and forth between a minus ak and ak with respect to time, so what you obtain is a sinusoidal signal, and that signal, or that waveform, is our xk of t. Okay. Okay, so there's a as we just see, there's a very nice relation between rotation with constant angular velocity and sinusoidal waveform. Okay, now let's apply our new definition on an example. Consider the following second order circuit that has reached steady state, sinusoidal steady state. So this is our circuit in sinusoidal steady state. Okay. So we have a capacitor, a resistor, and an inductor. And this is the input driving the circuit. Plus minus Vs. 1/3 ohms, 1 farad, 1/18 henries. And the directions are given as, this is the capacitor voltage, VC. This is our inductor current, IL. This is IR. Okay. And Vs of t is cosine 3t volts, suppose. And here we have the source current, let's call it IS. IS is minus IL. Okay. Now, it's easy to compute the following particular solutions. So we're not going to worry about the computation. We will talk about that later a lot. Okay. So let me directly write down the particular solutions of all the signals in this circuit that has reached sinusoidal steady state. Okay. So signals, by signals we mean the functions in time domain. We have 4 components, okay, so that makes 4 currents and 4 voltages. So we have a total of 8 signals, okay. So although it's a little bit boring, but for the sake of completeness, let's write down all those 8 signals, starting from the inductor current. IL of t is, or can be computed, or can be measured if we construct a circuit in the lab. 6 cosine 3t amps. IRT is 3 times square root of 2 cosine 3t minus 45 degrees, or pi over 4 radians amps. ICT, capacitor current, 3 square root of 2 cosine 3t plus 45 degrees amps. IST is minus ILT minus 6 cosine 3t amps. And then we have the voltages. VL of t is minus sine 3t. Okay, so by convention, we express everything in order to go to the phasor domain. We express everything, okay, in terms of cosine. So we can write this sine as cosine 3t plus pi over 2 volts. VRT is square root of 2 cosine 3t minus pi over 4 volts. VCT is the same as VRT, they are parallel components. Square root of 2 cosine 3t minus pi over 4 volts, and finally the input is cosine 3t volts. Okay. Now, for those signals, let's quickly obtain their phasor representations. Okay. Phasors. These are functions, but now we can express those functions as complex numbers, constant complex numbers. So we have IL, okay? Note that by convention we capitalize the time domain letter IL. So IL is the magnitude 6. This is 3t plus 0 phase, therefore it's 6e to the j 0. So that's the phasor of IL, and we can write it in rectangular form, and it's simply 6 plus J0. Okay, so we have 6 amps. IR, the phasor of the resistor, is 3 square root of 2. This is the magnitude, and the phase is e to the j pi over 4. E to the j pi over 4. Okay, and that in rectangular form can be written as 3 plus J3. Okay, and then we keep the units amps. Okay, for the phasors. Then we have IC, which is e to the minus j. Excuse me, so this is minus here and this is plus, so that makes a minus here. And here we have 3 plus J3 amps. IS is, okay, so this can be written as, note that here we want a positive magnitude, therefore this can be written as 6 cosine 3t minus pi or plus pi. So this equals therefore 6 e to the j pi in polar coordinates, and which is minus 6 plus J0 amps. So those are the currents. How about the voltages? We have the following phasors. This is cosine 3t plus pi over 2. Therefore, the magnitude is 1 and the phase is pi over 2. Okay, so this equals 0 plus j amps in rectangular form. And VR is, the magnitude is here, square root of 2, and we have e to the minus j pi over 4, okay, which can be written as 1 minus j amps. VC is the same as VR, so we have square root of 2 e to the minus j pi over 4, which is 1 minus, excuse me, these are volts, clearly. Okay, volt, 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 and finally Vs, the phasor of the source, is e to the 1 times e to the j0 in polar coordinates, and in rectangular coordinates is just 1 plus j0 volts. Okay, so these are the signals and these are the corresponding phasors. What's the frequency of oscillations? It's 3 radians per second. So this set of information plus the information regarding the frequency, omega equals 3 radians per second, is sufficient to, from the phasors, reconstruct the signals. Okay, now let's obtain the phasor diagrams. Okay. Phasor diagram. So let's keep all the voltages on one diagram and all the currents on another diagram. For the currents, okay, so let me mark the complex plane. This is real, this is imaginary. Okay, so let's obtain the currents. Let's draw the currents on the phasor diagram. So what we have is, we have IL. IL is 6 amps. So this is, let's say, 6 minus 3 minus 6. This is J3 and this is minus J3. Okay. So IL is this vector here. Okay. What's IR? IR is 3 plus J3, 3 minus J3. So here, this is R, this is IL, this is IR. And we have IC, which is 3 plus J3. Okay, so we're talking about this vector, and this is our IC. And finally, what's IS? IS is minus 6 plus J0. So this is our IS. Okay, so these are the phasor diagrams of all the currents in our circuit. So let's do the same thing for the voltages. Real, imaginary. We have VL, we have VS, and here we have VC and VR. So this is J, this is 1, this is minus J. Okay, so VL, VS, and here we have VC, VR. Now, if you look at this vectors, we know that the sum of IC and IR, these two vectors, okay, give us IL. Okay, so note that IL, the phasor, equals IC plus IR. Okay, these two vectors, when summed, give us IL. And as for the voltages, we see that Vs, this vector can be written as the sum of VL plus that vector, which is Vc plus VL. Okay. Now, if we look at the circuit and this equation, or write, for instance, KCL at this node, we see that IL equals IC plus IR. IL equals IC plus IR. Whereas that is a time domain equation. Now we're talking about phasors. So that immediately suggests the following very interesting question. Does KCL hold for the phasors of the signals? Okay. Likewise, here, this voltage of the source equals the voltage of the inductor plus the voltage of the capacitor. And that, so that equation, we have the same equation also for the phasors. Vs equals Vc plus VL. So that brings the question whether KVL holds in phasor domain. Okay, and the answer is yes. So in other words, this is not just a coincidence for our special example, but we have KCL and KVL holding in phasor domain in general. And let's quickly show that that is the case. So here is our claim. Phasors of currents satisfy Kirchhoff's current law. Okay, here is the proof. So in some circuit, we have a bunch of currents satisfying the current equation. Okay, let some currents satisfy KCL. Suppose we wrote KCL on some node and we obtained the following equation: I1 of t plus I2 of t plus In of t equals 0. Okay, some KCL equation. So from this equation, let's now obtain the phasor of I1 plus the phasor of I2 plus and so on up to phasor of In must equal to 0. Okay. So the real part of I1 e to the j omega t plus real part of I2 e to the j omega t plus real part of in e to the j omega t equals 0. So what we did, we rewrote this equation using phasors. This is how we construct I1 of t, this is how we construct I2 of t, and so on. Okay. So that yields, or can be written as, since real operator is a linear operator, we can write this as I1 e to the j omega t in e to the j omega t equals 0. Okay. And that can be written as I1 plus I2 in e to the j omega t equals 0. And from one of our identities that we have seen earlier, this is possible only if this thing is 0. Okay, so that yields I1 plus I2 plus in equals 0. So if the signals, time domain signals, satisfy KCL, then their phasors should also satisfy KCL. And the same holds for, not surprisingly, the voltages. In other words, phasors of voltages obey Kirchhoff's voltage law.